This helicopter is searching for metals, not just veins at the surface, but deposits at depth. It's collecting data by sniffing the ground. The samples it picks up contain traces of over 20 elements, and these can indicate ore bodies at depth. In minutes, the helicopter does what ground-based prospecting will take weeks to do, finding concealed deposits that would otherwise remain hidden. It's a long way from the old idea of striking it rich. Within a few years of Jackson's discovery, the surrounding hills were riddled with mines. The area became the richest square mile on Earth. Thousands trekked here from as far afield as the tin mines of Cornwall, all dreaming of quick riches, but most ending up as labourers working in company mines. Settlements sprang up. A series of classic mining boom towns was born. But like all booms, this gold rush eventually went bust. Those who could moved on, joining other gold rushes. They left behind some harsh reminders of the hard lives of these early miners. These derelict sites remind us also that eventually all mines become exhausted. No mine can last forever. But the demand for minerals continues, and the only way to keep up supplies is to find new deposits. On the ground or in the air, the task is the same for all prospectors. Cover rapidly as much suitable ground as possible, sample it carefully, rejecting barren ground, and hoping to find traces of valuable minerals. Even today, here in Colorado and all over the world, traditional panning continues. And from traces in the pan, the hope is to find the source of the minerals. And if you found a mother lode as rich as this, you'd have a bonanza. There are plenty of rich alluvial deposits of gold and other metals, like the tin ore cassiterite, for instance. And they can be found by panning and they're easily mined. But for most metals, the biggest and richest ore deposits are in solid rocks, from thin gold veins a few centimeters across to porphyry copper deposits that may be kilometers in diameter. Let's look at a specific example. There are rich ores of these two metals, gold and copper, in Colorado in the western United States. The first gold discoveries, the yellow circles, were around Central City, and the search for gold uncovered ores of many other metals, including silver, grey segments, molybdenum, pink, lead, blue, and zinc, purple. This part of the Rocky Mountains has produced many billions of dollars worth of metals since those early discoveries little more than 100 years ago. The size of the blobs on this map is related to the cumulative value of the metals produced. The largest, over $1 billion, the smallest, less than $100,000. The geological setting of these deposits is now very well known, because the region's been intensively mapped by geologists. At first glance, this all looks horrendously complicated, and in detail it is, but the broad picture isn't so difficult to see. This line is the Rocky Mountain front. East of it are flat-lying Mesozoic and tertiary sediments a couple of kilometers thick, underlying the vast prairies of the Midwest. On the other side of the front, there's a complexly folded and partly metamorphosed sequence of sediments and volcanic rocks. They range in age from Precambrian to Mesozoic, and they've been intruded by a variety of plutonic igneous bodies, mostly granites, granodiorites and diorites. All the metal deposits are found to the west of this line, the Rocky Mountain front. The Colorado area is an obvious example of a rich metallogenic province. It lies here, in the Rocky Mountain belt, which is part of this great system of young mountains that goes all the way down the western side of North and South America. Metallogenic provinces all along this great chain have got metal ores similar to those in the Colorado province. And that's because the geological environment is broadly similar all the way down. Now, the geological setting of these young mountains isn't unique. The processes that formed them and concentrated the metals in them have occurred on comparable scales several times in the geological past. For instance, much of northern Britain is part of such a mountain belt, formed about 400 million years ago. And in fact, the continental crust as a whole is largely made up of the remnants of these ancient mountain chains. So there are metallogenic provinces to be found in many parts of the world. That includes a seabed, of course, but that's another story, and we'll stick to continental crust. Now, the trouble is that the geological information is very sketchy over huge areas. This compilation was made some years ago now, and it doesn't include the communist bloc countries, but its message hasn't greatly changed. Only about 30% of the Earth's land surface has been geologically mapped on scales that are useful for any kind of detailed exploration. And it's detail that we want, because even the largest metal deposit is only a pinprick on this globe. So it's difficult enough to be sure of finding big deposits even when they're exposed at the surface. Smaller deposits beneath the surface, gold veins for instance, will be a lot harder to find. And we're not just talking about remote parts of the world. Even those areas that are extremely well known geologically can still come up with surprises. Geologists have mapped here in Snowdonia for decades. And copper, gold and other metals have been mined for centuries. And yet, in the early 1970s, a porphyry copper deposit was found here. It's not a big one by world standards, and it hasn't been mined yet because of economic and environmental factors. But it's still a pretty major discovery in an area that's been walked over by generations of geologists and miners. And so we can't even be sure we found all the ore deposits that exist in well-documented areas. It's going to be a lot more difficult in less well-mapped parts of the world. And the demand for metals doesn't get any less, so exploration is going to be directed more and more to comparatively unknown areas. When it comes to making a geological map, the field geologist can work most efficiently in areas of good exposure and high relief. By using well-exposed traverses and a pair of binoculars, a 3D picture can quickly be built up. But vast areas of the globe are nearly flat, and the rocks are mantled by soil and vegetation. A field geologist has to walk the whole area using only those few outcrops that poke through the veneer. It's an endless and frustrating task. Standard geological mapping techniques will continue to be important for many years to come. But to map the world this way would simply take too long. Since the 1960s, satellites have been used to map the Earth's surface in progressively greater detail. The complex images are stored on computer tape, but the geological information in them has to be manipulated and interpreted by geologists. This is an area of great economic importance in the Andes, about 50 kilometers across. It contains one of the world's largest copper mines. The processes which caused the mineralization altered the rocks into which the copper ores were introduced. The area of known mineralization is in the rectangle. The yellow-white surface is a mixture of clay minerals and iron oxides produced by the alteration process. There are plenty of other pale rocks in the area, but most contain only very highly reflective clays and they don't indicate mineralization. As far as the eye is concerned, both kinds of pale rocks look exactly the same. But altered zones known to be over copper ores can be identified. And the flashing white square can be superimposed on them. The computer can be instructed to analyze what is in that square and then find all other identical picture cells elsewhere on the image. The iron-rich minerals can be detected because their high red reflectance masked from the eye by brilliant white is still sufficient to be noticeable to the computer. Most of the pale areas are ignored and the clusters of red dots highlighted by the computer are targets for exploration. In a follow-up survey, more than 70% of these clusters proved to be associated with copper mineralization. Now that kind of success story is still rather rare. The more usual outcome is a form of geological map. And this is a part of India. Maps like these enable the geologist to distinguish areas of unpromising ground from areas that may be favorable and worth exploring, because they contain structures or rock types that are similar to those in well-known metallogenic provinces elsewhere. But even those are still big areas, and you've seen that our mineral targets are relatively very small. Here's an idealized hydrothermal vein associated with a granite. If the vein outcrops at surface, it can literally be tripped over by the itinerant geologist or prospector. Such veins are often found because water courses cut through them, and fragments are dispersed downstream. And those traces may still be present even if the vein's covered with soil. And buried veins can be detected by indirect methods. Airborne geophysical techniques can locate large veins, and ground-based surveys will define them more precisely, as well as locating smaller veins, always provided that the minerals have properties consistent with the technique. Carefully planned ground-based geophysical surveys can find small ore bodies even under a thick cover of superficial deposits. These geophysicists are using the induced potential method to locate sulfide ore bodies. But of course, geophysics isn't the only tool used to search for buried veins. The soil itself will contain increased concentrations of metals in the vicinity of the vein. A leading expert in geochemical exploration is Tony Barringer.
The mining geologist looks upon an ore deposit, certainly a hydrothermal ore deposit, as occurring in a plumbing system in which solutions have migrated upwards, and they've carried in those solutions large amounts of metals which have become deposited in a favorable zone for forming the ore deposit. But generally, once those solutions are deposited, they carry on up through a leakage pathway towards the surface, so that there are traces of the metals that were deposited still retained, and they leave a fingerprint, a dispersion halo, as the geochemist calls them, going upwards above the ore body towards the surface, so that even if an ore body is not directly outcropping, and it may be down several hundred feet, you will still get a geochemical halo above it.
Ideally, the exploration geochemist would like all mineral deposits to lie in arid areas. That's because, in such regions, the rocks are either exposed to the surface or have been weathered to form soils in situ. Such residual soils contain chemical evidence of possible deposits below, and geochemistry in arid areas is relatively straightforward. The task is much more difficult in wetter areas with dense vegetation. The same applies to areas covered in thick, glacially derived soils. Here, any mineral deposit will be masked by clays and gravels transported by glaciers. The geochemist carries out a biogeochemical survey of the vegetation, as well as geochemical surveys of the waters moving through this blanket of glacial material.
These are the most difficult applications of geochemistry, but people are starting to make sense out of it, and they're getting valuable methods, developing valuable methods of using geochemistry to supplement the geophysical techniques which are able to cope reasonably well with these glaciated terrains.
The samples from geochemical exploration may be soils, stream sediments, or stream waters. During analysis of soils and stream sediments, it's very important to take a representative portion of the sample because only 15 milligrams can be analyzed from the 100 or so grams collected. Fine grinding ensures as homogeneous a sample as possible. The sample's compressed into a pellet and placed in an emission spectrometer, which analyzes a wide range of elements rapidly and cheaply, and that's essential in this kind of survey. An electric arc excites atoms in the sample, which emit a light which is characteristic wavelength for each element. The intensity of the emission is proportional to the concentration of the element. It's read on a spectrometer and stored in a computer-readable form. Geochemical surveys can cover large areas economically and quickly. For instance, all the data in this atlas was compiled in a single field season. It was prepared by the Applied Geochemistry Research Group at Imperial College, and it covers the whole of England and Wales. The maps show the concentration at the surface of some 30 elements. Now, the man who pioneered rapid geochemical survey methods and was primarily responsible for this atlas is Professor John Webb, and he found some interesting correlations with mineralization.
Just for an example, the maps that everybody knows about the distribution of the granites in the southwest of England, and these are shown here by the map for nickel, where the granites naturally show up as blue, dark blue colors, which means very low values of nickel. And you will see the lizard here, where the nickel is obviously high, and that's related to the basic maps. Now, returning to the granites, the nickel shows where the granites are. But now look at lithium, and you will see now that only one of the granites, that's the St. Austell granite, a little bit of the Bodmin granite, and a small part of the Dartmoor granite, lithium is high. And those are associated with the distribution of chinic clay.
Well, rapid regional geochemical surveys can be used to define areas for more detailed follow-up surveys with more closely spaced sample points. But those surveys always involve a lot of tedious work by people on the ground, and that's something that Tony Barringer has tried to remedy.
We've always wanted to do geochemistry from the air to match up with our airborne geophysics, and we've striven very hard to develop a method. One of the most promising techniques has been that of sniffing the surface of the ground, not so much for gases, but for the fine dust, the particles that occur on the surface. What our research has shown is that you can get very good geochemical anomalies developed in the top millimeter of the ground. And there are a lot of special processes that exist there. The evaporation of water at the surface, which deposits salts, which carry the signature of the underlying soils, and mineralization if it's there. Since we have always been interested in trying to develop airborne methods for geochemistry to match with our airborne geophysical methods, we devised a method which uses a pipe beneath the helicopter, a very tough plastic flexible pipe on a flexible mount that the helicopter pilot drags along the surface. Now, he can either drag it continuously or he can dip it down and touch the surface, for example, 5 times a kilometer. And every time he does that, he sniffs the surface and it goes up into the aircraft onto a sticky tape recorder, which is exactly like a magnetic tape recorder, except it's sticky tape. And we get spots all the way along this tape where he's touched the ground. That tape is then sent back to our lab where the tape is hit with a laser beam. The tape is transparent to the laser beam, but the particles are not, and the soil particles are vaporized into a plasma spectrometer system which causes the material to emit spectroscopically so that we can read up to 25 elements simultaneously, and we can do this every 3 seconds. In the course of a day's flying, we'll fly typically about 100 kilometers of survey, and we'll do typically 5 samples per kilometer, which gives us 500 samples that we can analyze in half a shift. and we can put all those analyses onto magnetic tape as they're analyzed, and they're ready to go directly into the computer for plotting and for statistical analysis in the computer. So we have two advantages. Firstly, we can move at very high speed in reconnaissance geochemistry, and secondly, we can analyze very quickly. We have the sample already prepared for us, so that the time frame for carrying out the analyses, multi-element analyses, is greatly reduced. So it turns out to be very fast in the field and in the lab.
Well, obviously, this rapidly growing body of data can only be handled by computers, and by feeding in also all the older existing information from geological maps, from geochemical atlases, from mining records and so on. The computer provides a very powerful way of narrowing down the search. And those methods can also be applied to existing mining areas. Back in Colorado, you wouldn't think there was much more to be found in the way of ore deposits. But I said earlier that even well-known areas can come up with surprises. People are still looking for ores in Colorado, and this part of the state was thought to be a promising area on the basis of known geology and other information. Now, by computer processing of topographic information and gravity data, and then integrating that with the results of airborne spectral scanner surveys, a large new porphyry molybdenum body was found at Mount Emmons. That's not altogether surprising, perhaps. It does lie close to an extension of this line of major deposits. But the point is that it was only discovered in 1983. But in the end, the exploration geologist is after this: drill cores that tell him he's found an ore deposit. It can cost up to several $1,000s a meter to get drill core. So the better your exploration, the lower the costs of your drilling, and the greater your confidence that you've got it right. But even this isn't the end of the story. Your ore deposit can be the biggest in the world, but if there's no demand, it'll stay in the ground. Only if the demand is there and the price is right will your ore deposit become a mine.